Long before scientists could see atoms, they learned how to listen to them using light. Every substance interacts with light in a unique way, and hidden inside those interactions is a chemical fingerprint. Spectroscopy is the reason chemists can identify substances without touching them, simply by reading how matter absorbs, emits, or scatters light. This is the learning studio, where chemistry is explained as a way of decoding nature rather than memorizing facts. And after understanding how analytical chemistry makes the invisible measurable, the next step is to see the most powerful tool behind that ability: light itself. Most people think spectroscopy is just colorful graphs or rainbow-like spectra, but in reality, it is a direct conversation between light and atoms. For example, when a doctor scans tissue, when astronomers analyze the composition of stars, or when chemists identify unknown compounds, spectroscopy is translating light signals into chemical identity. No cutting, no contact, just information carried by photons. At the atomic level, the mechanism is precise. Atoms and molecules can absorb or emit light only at specific energies. These energies correspond to changes in electron positions, molecular vibrations, or atomic motions. When light of the right energy interacts with matter, it is absorbed. When matter releases energy, light is emitted. The resulting pattern acts like a barcode that uniquely identifies a substance. This idea began with Isaac Newton, who showed that white light contains a spectrum of colors, but it became chemically powerful through Joseph von Fraunhofer, who discovered that each element produces its own distinct set of spectral lines. These discoveries proved that light could be used as a chemical identifier long before modern instruments existed. As spectroscopy advanced, scientists learned to read increasingly subtle signals. Infrared spectroscopy revealed molecular vibrations. Ultraviolet and visible spectroscopy explained electronic transitions. Later, techniques like nuclear magnetic resonance and laser spectroscopy made it possible to map molecular structures with extraordinary detail. Light became a probe capable of seeing inside molecules themselves. This capability transformed science and technology. Spectroscopy allows chemists to verify molecular structure, detect trace contaminants, monitor reactions in real time, and even analyze materials on distant planets. Entire fields, from astrophysics to medical diagnostics, depend on the same principle. Matter reveals its identity through how it interacts with light. Spectroscopy also reshaped chemistry's confidence. Instead of guessing molecular structures, chemists could confirm them. Instead of assuming purity, they could measure it. Instead of inferring composition, they could read it directly. Light turned chemistry into a science of direct evidence. And once we understand how light can reveal the identity of matter, the next question naturally follows. If chemistry can read molecules so precisely, then how does it explain the chemistry of life itself, where molecules interact with extraordinary complexity and purpose? That question takes us directly into the next episode, where we explore biochemistry and the molecular foundation of living systems.